Let's go on to the next slide. This is non-ideal, and also I should probably say non-standard conditions. So let's look at these equations, see what they come from. And down here is where we're talking about non-ideal behavior. Let's first talk about this. So let's first start by realizing that G is a function of temperature, pressure, and number of moles. It's a function of pressure at constant T and number of moles. So now we're going to say, how does G change? Well, that's how G changes with pressure at constant temperature, number of moles, times dP. And, let's make the assumption this is an ideal gas. No, actually we don't. We don't have to make the assumption it's an ideal gas. Remember from, I don't know, two lectures ago perhaps, that this is volume. How G changes the pressure, constant T, is volume. We can write this as V dP. Let's integrate this. Let's integrate this from, say, G1 to G2 dG. This will be the integral from pressure 1 to pressure 2 of V dP. Let's make the usual assumption we have an ideal gas. So we can replace V with nRT. So this will be the integral from P1 to P2. V is nRT over pressure dP. And this we know by now is just integral, so we have delta G, G2 minus G1, is equal to nRT times the natural log of the final pressure over the initial pressure, where the final pressure is, let's be explicit, this is G2 minus G1. So final pressure corresponds to G2, initial pressure corresponds to G1. All right, now we're going to introduce the concept of standard state. So standard state, we're going to associate G1 with a standard state. We'll give that G with a 0 up there. That means standard state. And we're going to use, and P1 then will be the pressure at the standard state. Pressure and standard state in PChem, the standard state pressure is 1 bar, which is close to 1 atmosphere, but not quite equal to it. What does this mean? This means we're going to measure free energies relative to some standard state. So we're always going to have a reference for a standard state. So let's just rewrite that in the new notation. Delta G, measured from some standard state, is equal to, well, let's just be more explicit, G2 minus G0. That's equal to nRT times the natural log of P2 over P0. And note that's 2 there, so we really don't need to carry around that 2G. So G will automatically be 2G minus G0 is nRT times the natural log of P2 over, P0, where that's the standard. Furthermore, we know that mu we defined was how G changes with N at constant temperature and pressure. So if we take the derivative of this with respect to N, we have how G changes with N minus how G0 changes with N, and that's equal to derivative that the N will go away. This is just RT times the natural log of P over P0. We'll call this mu, the chemical potential, and we'll call this mu0, the chemical potential in the standard state, which we defined was 1 bar for gases. So if we combine these, there we go, G minus G0, or let's rewrite this as G is equal to G0 plus nRT, natural log of P2 over P0. And we write this as mu is equal to mu0 plus RT, the N goes away, natural log of pressure, don't need to carry the 2 around anymore, divided by P0. So that's where these two equations come from. It's for ideal gases And we said that, well, we just used this handy-dandy equation here. That came in handy. See, when we learned that a while back, it's coming in handy. We integrated that, and we found that free energy depends logarithmically on pressure, as does chemical potential. That's for ideal gases. What happens if you have a non-ideal gas? What you do is replace the pressure with something known as fugacity. That's a weird name, fugacity. And fugacity is defined as the pressure times the fugacity coefficient, which you can sort of think of as a fudge factor. So what this is the symbol phi. What phi does is correct the pressure so that you can use fugacity in here. So it's as if you're using the ideal gas equation, but you're using it with a correction factor to take into account the gas is non-ideal. This sort of corrects it back up to what it would be if it were ideal, and you can use ideal gas equation. All right, so when you replace pressure with fugacity, that's an F there, that's an F there. This you can maybe calculate, but more generally it's measured experimentally. And fugacity would be a function of pressure and temperature. To show that the fugacity coefficient depends upon the gas. Once upon a midnight weary, while I was pondering weak and weary over many a quaint and forgotten book of lore, I found this article, Fugacity Coefficients for Hydrogen Gas. And this is the American Journal of Science way back in 1964. And here's some data. There it is. Fugacity coefficients for hydrogen gas, as a function of pressure and various temperatures here. Temperature, this is in degrees C, and this is in atmosphere. What we see is a fugacity, well, this is for atmosphere, and the ones in italics are for pressure in bar. And what we see is the fugacity coefficient varies depending on what pressure you have and what temperature you have. And for hydrogen, under these conditions, the fugacity coefficients are greater than 1. Look at all that data. Cool. So they're all greater than 1. That's kind of cool. So what we've shown here, fugacity coefficients, you determine those experimentally. You multiply those by the pressure of the gas, the actual pressure of the gas, and then you get a fugacity, which you then plug into these in place of the ideal gas pressure. You plug in the fugacity. Let's sort of do that here. So we said the fugacity F was some fudge factor called the fugacity coefficient times pressure. Now for an ideal gas, of course, the fugacity coefficient will just be equal to 1, so that the pressure you plug in, or the fugacity you plug into those equations here, will just be the actual pressure you measure the gas. But for hydrogen and a lot of other gases, for H2, etc., the fugacity coefficient is greater than 1. What does that mean? Well, the pressure for an ideal gas, you're going to have to multiply that by a number greater than 1. It is as if these real gases don't have enough oomph, and you got to multiply by a number greater than 1 to give enough oomph in order to put it into those equations we just had. So that's what that means. That's how you take into account non-ideal. Typically you put in a fudge factor, and when we talk about solutions, the fudge factor will be called the activity coefficient. Here it's called the fugacity coefficient.